Bismillah ar-Rahman ar-Rahim. Welcome, my dear students. This is last lecture for our course Numerical Analysis, and our chapter today is chapter 4, Numerical Integration. The first questions we shall discuss it is why we discuss numerical integration. As we study integration in second term of first year in Faculty of Education, some of integrations can be solved analytically, such as integration x squared dx, cosine x dx, but some integration cannot be solved analytically, such as integration of x e x to the power 3 dx, or to the power 4, or to the power 5, and so on. Indeed, most of the integrations cannot be solved analytically. Most integrations cannot be solved analytically. And another situation, if the function is given as a table, and we want its integration, so we know that the integration in meaning is the area under the curve. The integration in meaning is area under the curve. So if we have a table of the function, we can evaluate the area and so evaluate the integration, and this will be done numerically. Let's see the first item of our chapter, the basic trapezoidal rule. The basic trapezoidal rule. Trapezoidal means this shape. This shape is trapezoidal. Two parallel lines, and the another two lines is not parallel, so it is rectangle, but two of its length is not parallel. So this is the meaning of our title, trapezoidal rule. To evaluate the area under the curve, we have a curve f of x, and 2 points A and B. Here is A and here is B, and here is the value of the function at A, which is f of A, the value of the function at B, which is f of B, and then we draw a line from these 2 points and take it as an approximation for the curve. So we evaluate this area, and this area can be evaluated as a multiplication of average base, which is the two bases f of A and f of B, times the altitude P minus A, which can be named as H, B minus A, which named as H. So we take H equal P minus A, and then we have the average of the base, which is f of A plus f of B over 2 times H, or we can write it as H over 2 multiplied on f of A plus f of B. This is the trapezoidal rule to evaluate the integration of the function, integration from A to B, f of x dx. T1 equal h over 2 f of a plus f of b. This is the rule. Example. Approximate the integration from 0 to 1 dx over 1 plus x squared using the basic trapezoidal rule. Then evaluate the numerical error. Answer. f of x here is 1 over 1 plus x squared. A, the first point of the area, which is a equal 0. The last point of the area, which is b equal 1. F of a means f of 0, and if we substitute with x equal 0 in the function, we have 1 over 1 plus 0, so it's 1. F of b, which is f of 1, 1 over 1 plus 1, or 1 over 2. So applying the trapezoidal rule, h, which is the distance between b and a, which is b minus a, which is 1 minus 0, so h equal 1 over 2. F of a, which is evaluated as 1, and f of b plus, which evaluated as half. So this is the substitution, and the result in all is 0.75. This example is understood, my dearest student. Do you understand?
Yes.
Okay. To obtain the numerical error, we must have the exact solution. The exact solution is for the integration from 0 to 1 dx over 1 plus x squared is tan minus 1 for the value 1, which equal pi over 4, and which equal 0.785, and so on. So the numerical error is subtraction the exact solution from the numerical solution, or the opposite. So we take the absolute value, and here is 7.75 the numerical solution, and here is the exact. We subtract, and then the result is 0.035, or 3.5 times 10 to the power minus 2.
Doctor,
Yes.
I don't understand the error.
You don't understand
The error.
the error. The rule is subtraction.
No, 10 negative 1. Why?
This is the
why?
exact solution. This is the exact solution. Okay, do you remember the course of integration in the second term of the first year in education faculty? This is
No, sir.
true. You don't remember. So I write it here. We have d over dx tan minus 1x equal 1 plus x squared, and then the inverse integration dx over 1 plus x squared is tan minus 1x plus constant.
Okay.
So the integration 0 to 1, we take the upper bound minus the lower bound, and tan minus 1, 0 is 0. Okay? Don't worry.
Okay.
Now the accuracy for this rule is not good enough. We have 3.5 on 10 to the power minus 2. So we must obtain greater accuracy. So to improve our estimate of integration, we divide the interval into two sub-intervals. So we have an integration from 0 to half plus an integration from half to 1 for the same function. If we do that, we shall apply trapezoidal rule 2 times, one for the first integration and the second for the second integration. For the first integration, here is h, which is half minus 0, and so is here h is 1 minus half, so h equal half, h equal half, and f of 0, which is 1, f of half, so we have this is the function 1 over 1 plus half square, 1 plus 1 over 4, 5 over 4, so it's 1 over 1 plus 1 over 4, or 5 over 4. In the second integration, we have h equal half over 2, f of half plus f of 1, and so the results in all is 0.775. 0.775. If we evaluate the exact solution and the error here is 0.01 times or equal 1.1 times 10 to the power minus. If we compare the error in this situation and the previous, in the previous situation the error was 3.5, and here we have 1.1, so the error here decrease 1.1, 3.5, so times 10 to the power minus 2, so E1 is greater than E2. Okay, the composite trapezoidal rule. Before that, do you understand example 2? My dearest students, do you understand example 2?
Yes, doctor,
okay.
Yes.
Okay. Next title is the composite trapezoidal rule. If we divide the interval from A to B to n sub-intervals with equally spaced points, xi equal a plus I h. Here is the graph. Here is a.
Doctor, I just have one question, please.
You can.
When we calculate the error, will we use the rule of the error or the rule of the greater accuracy?
We search about good accuracy. Okay?
Okay.
Here is our graph. Here is A, which we shall name as x naught. Here is B, which is named as xn. F of A, f of B, and we divide the interval into sub-intervals by the points x1, x2, and xn minus 1. The points are located as xi equal a plus ih, xi, x1, x2, and 2xi. H will shall evaluated by the rule h equal p minus a over n. P minus a over n. P the last interval, and a the first, and n number of sub-intervals. Number of sub-intervals. Okay. So we evaluate in each sub-interval the rule of basic trapezoidal rule. In each sub-interval we apply the trapezoidal rule, the basic trapezoidal rule, and add them. So we have here Tn equal integration from a to x1, from x1 to x2, and so on to the last one, which is integration from xn minus 1 to p. And here is it. The first integration is h over 2 f of a plus f of x1. The second, h over 2 f of x1 plus f of x2. And the last, f of x n minus 1 plus f of b. If we add these terms, we have f of a one time, we have f of b one time, but we have f of x1 two times, here, one here and here, and f of x2 will be two times here and in the next brackets, and up to f of x n minus 1 we have two times here and the previous brackets. So the result is f of a plus 2 f of x1 plus 2 and so on to 2 f of x n minus 1 plus f of b. One time f of a, f of b, and 2 for all the entire points. So
Sorry, doctor, I don't understand.
Look at this graph. We have f of a here, okay?
Okay.
And the area or the basic trapezoidal rule for the first sub-interval, we have f of a plus f of x1, okay?
Okay.
For the second sub-interval, we have f of x1 plus f of x2, okay?
Okay.
And so on. The last interval, we have f of xn minus 1 plus f of b, okay?
Yes. Okay.
If we add all of them, we have one time f of a, f of b, and f of x1 two times. It will be in the first
yes, I understand.
in the first interval and the second, and so on, okay?
Okay.
So the basic trapezoidal rule, the composite trapezoidal rule is Tn equal h over 2 multiply n or times f of a plus f of b one time plus 2 times the summation from I equal 1 to n minus 1 f of x. This is the trapezoidal rule. The estimated error here is minus b minus a times h square over 12 f double dash, the second derivative, evaluated at c, which located in the interval from a to b. This is the composite trapezoidal rule. Let's take an example. Here is the table, function evaluated as a table, and we need its integration from 0 to 1. The result is, here is the rule, h equal xi plus 1 minus xi. Here is xi, here is x1, and here is x0. The distance between them are 0.2 minus 0, which is 2. So h here equal 0.2, and another rule is h equal p minus a over n. Okay, h equal p minus a over n. So we have p, which is 1, a, which is 0, and n number of points. What number of points in this table, please? How many points in this table?
6 points.
6 points, and we name it as x0, x1, x2, x3, and x4. Okay, So it is 1
Okay.
over n, so 1 over 5, so the result is a 0.2. Here's h. So
Doctor, but where is B in the table?
the last point. The first point,
The last
is
point
A,
is B.
the last point is B.
Okay, okay.
F of A, let's I think that this is f of A and this is f of B. I'm sorry, this is f of A, which is 0, and this is f of B, which is a 1.
1.
Okay, let's write it. Here is f of A plus f of B, and here is 0 plus 1 plus 2, and 2 is multiplied on the summation of the all remaining values of f. 0.4, 0.16, 0.36, 0.64. Here is 2, and we sum in the bracket 0.4, 0.16, 0.36, and 0.64. Understand?
Yes.
Okay, the result here is 0.34. This is the T5 or trapezoidal rule taking 5 points. Here is the error, minus A minus B times h square over h over 12 f double dash of c. If we want to estimate the error, we apply this rule with n equal 5 and h equal 0.2. Here is it. He give me the exact solution or the exact function, which is x square. Okay, so f of x equal x square, f dash equal 2x, and f double dash equal 2. So RT equal A minus B, 0 minus 1 is minus 1 multiplied on minus, so the result is 1. H square 0.2 is about 2. Okay,
Yes.
12,
Okay.
and f double dash of c is 2. Okay, the result is 0.0667. This is the estimated error.
Doctor, one question.
Yes, you can.
Where did we get the f of c?
F of c. Here is in the question. Estimate the error for using trapezoidal rule to obtain integration from 0 to 1 x squared dx. Here is f of x. Okay. Here is f of
Okay.
x. So
This is f of x.
yes. And f of c, we have f double dash of c is 2, which doesn't depend on x or c. It's a constant. So we write it as it. Okay.
So f double dash of x. So x is equal to c.
Yes, we substitute with the value of c. Okay.
Okay.
We substitute by x by the value of c, and it doesn't change here since the function f double dash of x is constant.
Okay. Okay, doctor.
You have a good question. Okay. Now let us focus on the next rule for integration in this chapter, basic Simpson rule. Basic Simpson rule. In trapezoidal rule, we need 2 points to make a numerical integration, and here we take 3 points. The first point is A with f of A. The last point is B with f of B, same as basic trapezoidal rule. and we put in the middle a point x1 f of x1. The basic trapezoidal, the basic Simpson rule is integration from a to b of x dx equal s2 equal h over 3, not over 2 as trapezoidal. And here we have f of a, in the last we have f of b, same as trapezoidal. In the middle we have plus 4 f of x1. And x1 is the point in the middle from a to b, so it equal a plus b over 2. Do you understand?
So there's always one point in the Simpson rule?
In the basic
there's only one point
yes,
in the
yes,
middle of AB.
Yes, in the basic Simpson rule we have one point in the middle.
Okay.
H equal p minus a over 2. In the basic trapezoidal rule we have h equal p minus a. Here h equal p minus a over 2. This is the basic Simpson rule. Let's focus in the same example we take in the basic trapezoidal rule, integration from 0 to 1 dx over 1 plus x squared. Here is the graph of S2. Here is the point x1 in the middle, and here is x naught equal a, x2 equal b, and here is the graph. The green line is the estimated value, and it is near the function curve. So we shall see that the Simpson rule is accurate than basic trapezoidal. Let's evaluate f of a in our example. Our example here is the function is 1 over 1 plus x squared. So f of a equal f of 0, 1 plus over 1 plus 0, so the result is 1. F b equal f of 1, so the result is half. And x1 equal a plus b over 2, which is equal half. لحظة يا بنات وهكمل معاكم.
Okay.
ماشي. هنكمل يا بنات اعتزال.
Okay.
Okay. The numerical value is S2 equal h over 3 f of a plus 4 f of x1 plus f of b. So f of a equal 1, f of x1 equal 1 over 1 plus half over 4, and f of b equal half. So the result is 0.78333. Okay, this is the numerical evaluation Simpson rule for the integration. Do you understand it?
Yes, okay.
Okay, the exact solution again is 0.785 and so on. So the error, if we subtract from the solution, is 0.02 or 2.4 multiplied on 10 to the power minus 2. If we remember the result of trapezoidal rule in basic, it's 3.5. So here in Simpson rule is more accurate. Do you understand?
Yes.
The last item we shall take in this lecture is composite trapezoidal rule, and composite trapezoidal rule we shall just write the last here is last rule. We have Sn equal h over 3 f of a plus in the last here f of b. Okay, and we have here plus 4.
Doctor, I have a question. I'm
Yes,
sorry.
you can ask.
Is Simpson's rule more accurate than the greater accuracy rule?
Simpson rule is more accurate than trapezoidal rule. Yes. Yeah.
Okay, doctor. Okay, okay. I understand.
Okay. Plus 4 as the basic Simpson rule, and for here we shall multiply it on the summation of odd values of the function f of x1, f of x3, and so on. Plus 2 times the summation of even values of the function f of x2 plus f of x4, and so on. This is the composite trapezoidal rule. H over 3 f of a plus f of b, 4 times the summation of odd values of the function, 2 multiplied on even values of the function. And let us take an example to understand. Here is the example. The same example we take before, but we add 1 point to it. Please say to me what is in this table.
What is n?
Yes, number of points.
14. N is equal 14.
Number of points. Here is 1, 2, 3, 4, 5, 6, 7. Okay? Okay?
Okay.
And
We don't count the function of x. We only count x in the number.
we name the first number as 0. So we have 1, 2, 3, 4, 5, 6. So we have even values of n. Okay? F of a equal 0, f of x6 equal 1.14, and we shall name the odd values. The first one is f of x1, which is 0.04. The third one is 0.36, and the fifth is 1. Here is it. Here is it. X1. Okay, here is it x3, and here is it x5. Okay, the even we have x2 equal 16. Here is it, and x4 equal 0.64. So we add or sum the odd values here, which equal 1.40, and the even, which equal 0.80. So S6, which is Simpson composite Simpson rule, equal h, which is 0.2. H here is the distance between any 2 points of the values of x, so it's 0.2. Multiply on f of a, which is 0, f of b, which is 1.44, 4 on the odd values, which is 1.4, 2 on the even values, which is 0.80, and the result is 0.567. This is the result, and we can evaluate the numerical error. We can evaluate the if we have the exact solution is x squared, so the exact values of the integration is 567, and if we subtract the exact from the numerical, we have the result is 0. The rule for estimated error is minus b minus a times h to the power 4 over 180 f to the power f derivative order 4 evaluated at c. And if we evaluate, we have the first derivative of x squared is 2x, the second is 2, and the third and the fourth are 0. So we have r here equal 0, the same. So the numerical error is 0 and the estimated error is 0. I think that this is enough. We turn to the last item of this lecture, which is we shall write some MCQ questions of the items we teach in this lecture. Okay, anyone has any question? My dearest student, do you understand me? Bismillah ar-Rahman ar-Rahim. If we start MCQ questions for numerical integration, we shall take Simpson rule as an example, and you can take same questions for Trapezoidal Rule. This is our rule here, and we take it as MCQ. So we write it in the following manner: S2 equal h over a. Here is h over 3. F of a plus p on f x1, which is 4 f x1 plus f of b, where x1 equal a plus b over 2, a plus b over c, and h equal p minus a over 2 or b minus a over b. So we write as an MCQ true false question: a equal 2, which is false. A must equal 3. B equal 4. Here is B and here is 4, so it is 2. C equal 2. Here is C equal 2. D equal 4. D must equal 2, so it's false. Okay, I think that this question is understood carefully. For the example, to approximate integration from 0 to 1 dx over 1 plus x squared using basic Simpson rule, we have x1 equal half, h equal half, and s2 equal h over 3, which is half over 3, f a, which is 1, 4 f of x1, which 5 over 5, 4 over 5 plus half, and this is the last result. We write it as MCQ question. We write x equal a and h equal b, and s2 equal b over 3 plus 4c plus b equal e. A equal half, b equal half, c equal 4 over 5, d equal half, e equal 0.78333, and all of them are 2. I think also this question is understood. Composite Trapezoidal Rule. here is the composite trapezoidal rule in very easy manner. Sn equal h over 3 f of a plus 4 times sum of odd values of the function plus 2 sum of even values of the function plus f of b. So we write it in MCQ questions. Here h over 3 we write it h over a, and 4 here take it as b, and 2 take it in c, and the questions are a equal 3, which is true, b equal 4, which is true, c equal 2, which is true. For comparison of the error estimate in trapezoidal rule and Simpson rule, in trapezoidal RT equal minus a minus b times h square over 12 f double dash of c. In Simpson, minus b over minus a h bar 4 over 180 on the fourth derivative of f at c. If you write it as MCQ questions, we shall write a here instead of h square. So the question will be a equal h square is true, b here instead of 12, and c instead of f double dash. Here is it, b is 12 and c f double dash. In Simpson we have d instead of h to the power 4, and e equal 180, and f is fourth derivative, and all of them are true. I think that it's enough. Thank you. See you later. Assalamu alaikum.